but you're correct. Metal and a nonmetal. What's a covalent bond? Or sorry, let me try that again. Nonpolar covalent bond.
When atoms are the same.
Two nonmetals is kind of our standard definition, but that doesn't separate nonpolar covalent away from polar covalent. That just gets us the covalent classification. So we want something to kind of separate those two away from each other because they are distinct. So it's the same element to the same element. And the carbon-hydrogen bond is also classified as a nonpolar covalent bond. So those are some important distinctions within those. What happens for a polar covalent bond? What do we decide on that one? Sorry, what's that?
Two nonmetals that aren't like carbon and nitrogen or the same element.
True. So that was an awful lot of words. I don't want to write that many words. Let's try that again. Yeah, there we go. I like that one better. Everything else. It's not perfect, but it gets us darn close to those exact definitions based on our electronegativities. Right? And the reason we go through and subcategorize these has to do something with the structures and how they react. If we take a look at the bond connecting sodium and chloride, that bond is ionic. And one of our characteristics of our ionic bonds is that they don't share electrons. They transfer electrons. So sodium comes in with 1 electron, and our chloride comes in with 7. And what ends up happening? Sodium transfers its 1 electron to the chlorine. If it does that, chlorine has gained an electron, which means its charge becomes negative. Sodium lost an electron, so its charge becomes positive. So we have these distinct charges showing up, and it's these charges which predict something about, or we can use to predict something about chemistry, right? How the molecules react. If we go through and look at, let's just pick the carbon-hydrogen bond, the difference in electronegativity is so small that the electrons in that bond, right, the line connecting our carbon and hydrogen, are equally shared between the carbon and hydrogen. Which means what happens to the charge of the carbon? It's neutral. Right? It neither gains an electron nor loses an electron. So if we were going to try and represent that, right, we might go through and just do a 0 with a slash over the top of it to represent no charge building. Right, if we go through and now look at a polar covalent bond, now what happens? Let's pick O and H. The polar covalent is significantly different from the nonpolar covalent and significantly different from the ionic. Right, and if we go through to look at our electronegativities, there's a pretty drastic difference in electronegativity between the oxygen and the hydrogen. So what we'll do is push that to the extreme. Oxygen is way more electronegative than hydrogen. Just like chlorine is way more electronegative than sodium. So what charge builds on the oxygen? Negative. It starts to steal that hydrogen's electron. So we could go through and put a negative charge over the top of it. Well, if it becomes negative, it gained that electron, and it took it from hydrogen. So hydrogen necessarily must become positive. So what we're trying to do is show that we've got this kind of charge building, and that allows us to predict something about the chemistry of how that bond is going to interact with other molecules. Right? Except if I look at these drawings, I say an OH bond is what type of bond then? If I look just at the drawings, what does the OH bond most closely resemble? Ionic. Is it an ionic bond? No. So there's something wrong with my notation. Putting those charges on helps me understand the chemistry, okay, but it's not formally ionic, which means I don't have a negative and I don't have a positive. So what I want to do is change the notation now of my symbols to make sure that I can show that we do have these almost negative and almost positive charges without showing these formal charges, because the formal charges mean ionic bonds. So what can I add to the structure to make that negative and make that positive not really negative and not really positive? Okay, your textbook addresses this as the delta notation. All we're going to end up putting is a little delta symbol, okay, the lowercase delta, next to each of those. What did delta mean? Okay, we looked at that delta symbol, that capital delta symbol. So delta T was change in temperature. What's the lowercase delta mean? Pretty much the same thing. It's a change in the charge. The oxygen is changing to become more negative. The hydrogen is changing to become more positive. How do we know that the oxygen is becoming more negative and the hydrogen is becoming more positive? You have to know something about the electronegativities. Okay? So this is where knowing the trends in electronegativity can help you predict the delta notations. Now when we go through and look at this, we have three distinct ways to look at these bonds, okay, or address them as different types of bonds, and we have three distinct notations. In our ionic bond, when we show that, we show formal positives and negatives. And you'll notice what happened to the line connecting the sodium and the chlorine. Is it there anymore? No. Why not? Because the chloride takes the electrons from the sodium. If it takes the electrons, we don't have that formal bond anymore. Okay? What happens when we move to the nonpolar covalent bond? We still have that line showing the connection between the carbon and the hydrogen. And if we wanted to, we could specify zero charges on top. Okay? So we're now showing that that is not going to react very much because it's not charged. What happens when we look to the polar covalent bond? We still see the bond connecting the oxygen and the hydrogen. And we've added more information to it expressing something about the difference in charge between those two atoms. That one is more negative than the other. Which means we are starting to progress from a nonpolar situation to the extreme polar situation in the ionic bond. Since we're sitting somewhere in between, we have to come up with this odd notation in between saying we're getting these partial charges. Okay? Is there another way we could represent that charge system? Right, and as a hint, it's going to center around our polar covalent bond, so I'll erase everything else. One thing that we pick up in organic chemistry is we use arrows to show the flow of electrons. Where are the electrons moving to? Okay, so if I wanted to add an arrow to this, where would that arrow point to? What's that? Point to the oxygen. I'm trying to show the flow of electrons towards the oxygen. So we could say, with our arrow, that the oxygen is gaining those electrons. We add just a little bit more information to this. That extra information just happens to be one little line. What does that one little line represent? What's within that box? What symbol does that look like? It's a positive symbol. What charge was our hydrogen building? Our positive symbol. So we're showing the flow of electrons to our most electronegative element, and we're now also symbolizing our arrow a little bit further and adding that plus symbol so that we know that where our arrow started from, okay, is now becoming positively charged. Okay, so what we're trying to show is, again, just how the electrons shift within the molecule. That's it. Questions about that? Okay, this is something you are responsible for on exam 2. Okay. No questions? Whoops. Should have moved this slide so we don't have to go through it all. I put up these rules. And a lot of people didn't like these rules. That's fine. You don't have to follow them. You also don't have to get the answer right. Okay? If you want to get the answer right, follow the rules to the letter. It works. Okay? And we went through a couple examples with these on the next slide. We did CF4 already, and we did the NH4 plus already, right? There are questions about either of those two from last week. Should I go through and do those very, very quickly? Do those two again very, very quickly? Okay. CF4. Rule number 1, what do we do? Total of valence electrons. So we need to know how many valence electrons carbon has and fluorine has. How many valence electrons does carbon have? 4. How do you know it's 4? All right, we got a couple options. Good call. We could look at carbon being in column 14. All right, 14 minus 10 is 4. All right, so we can look at that. What's the Roman numeral at the top of carbon's column? Also 4. Guess what? It's also our valence electron count. Okay, so we don't have to know anything about electron configurations. Our valence electrons are told directly to us off of the periodic table. Pretty awesome. How do we actually go through and look at our valence electrons? We could go through and do the electron configuration. The electron configuration for carbon would be 1s2, 2s2, 2p2, which you should be that quick in finding out. Right? Our valence electrons are our highest energy level electrons. Where's our energy level in this notation? Our energy level is the 1 or the 2 in front. Okay, so we're looking at the second energy level being our highest number. Anything with that 2 in front is now our valence electron count. So we can now total the electrons. Where are the electrons represented? In the superscript or exponent, 2 plus 2 is 4. We end up with that magic number 4 again. Okay? So 4 valence electrons for our carbon. For our fluorine, how many valence electrons?
7.
7. How do you know it's 7?
It's in the 7th column.
I accept that answer. 7th column means 7 valence electron. What's the number of the column?
7.
17.
17 and then
Minus 10 gets us our 7. Roman numeral?
7.
7. Okay, if we went through and did the electron configuration, how many valence electrons are we going to find in that highest energy level?
7.
7. Lots and lots of 7s. Lucky number 7. Okay. Now the next question is when we're totaling our valence, we have to count the valence electrons for every single atom within our structure. How many fluorine atoms are there? How do you know there's 4? Because the subscript after F says 4. So that means whatever's directly in front of it, that's how many we've got. All right, so there are 4 fluorines. We could do that by adding fluorine in 4 times, or that's why you attend lecture. You never get that in the video. Maybe that's why you don't attend lecture, actually. We can do 7 times 4. Okay, 7 times 4 is 28 plus 4, 32. 32 electrons need to go into my structure. We now have to pick the central atom. What's our central atom according to our rules? According to our rule, I know, being the least electronegative. Which is least electronegative, carbon or fluorine? Carbon. How do you know that? Fluorine is the absolute most electronegative, which is actually why I picked this problem. Okay? So that simplifies it. The other option is that we look at our trends. Upper right-hand corner is the most. As we shift away from that right-hand corner, it becomes less electronegative. All right, so carbon's our center atom. What do we do next? Well, the abbreviated rules don't make it super obvious. We can scatter the rest of our atoms around it. Next step. Add our electrons to the most electronegative element. Which is the most electronegative element? Fluorine. So we will start putting our electrons on the most electronegative element. We're going to add them up to what point? Till it achieves a full octet. Its full octet is 8. How do you know it's 8? What's oct mean? 8. Why do you need to know oct?
For like molecular compounds.
For your molecular compounds and nomenclature. So it's something you're already supposed to know. 8 electrons need to go around each fluorine. How you decide to put them in isn't going to matter. So we could go through and put them in singly first and then double them up. Okay, remember we put them on the 4 faces of our squares around each of these. And we can drop all of our electrons into our structure. How many electrons am I at now? 24, right? Okay. We now have all of our electrons added into it, and we'll continue to add those electrons until we've achieved the total. Okay. How many electrons do we have in this? How many electrons can we put in? So we've achieved our total. That means we cannot add any more electrons to the structure. Okay. This is one's kind of nice because we don't have to worry about everything having 8 electrons around it, because everything does have 8 electrons. Okay. Any place that we have a pair of electrons between atoms will convert into the line. Remember, these are abbreviated instructions. The abbreviated, we're trying to show that line to represent what? A bond between atoms. And at this point, what we're looking at is just the 4 faces of our square. So all of those can be turned into a bond. Okay. Now that we've converted into a bond, we'll move to rule 6, satisfy your octets, which means we look at each atom and we say how many electrons are around that atom. So let's take a look at our first fluorine. How many electrons are around it? 2, 4, 6. How do I count the bond? 2. Okay, let's take a look at the carbon. How many electrons are around the carbon? 2 for our bond, 4 for the next bond, 6 for the next bond, 8 for the next bond. So the bonds will end up counting in 2 different situations for both atoms. Right? At this point, I've gone through and assigned or satisfied my octets all the way through. I don't have to worry about resonance because everything's got its octet satisfied. I also don't have to worry about formal charge. Okay? I put the strike through because that's actually how you calculate the formal charge per atom. We're making it simpler this time. You don't have to do it per atom. You just do it for the structure. Is CF4 charged? Should it carry a charge? No. How do you know that? Why is the answer no? Nothing to do with octets. You will find octets are always satisfied, even if you have a charge.
Is it because it doesn't have a plus or a minus next to it?
What do you mean? Where?
On the top right.
Look in the upper right-hand corner. The upper right-hand corner is where we specify the balance of our electrons. If it's nothing is written in the upper right-hand corner, what's the charge? 0. Which means when we look at our structure, we are now done with our Lewis structure. Yippee! I went through that one kind of slowly, so let's go through the next one a little bit faster. Questions on that one before I erase it all? Okay. Bless you.
One question.
After I erased it all.
No, it's fine, it's fine. When you're adding the electrons to the fluorines, the most electric activity,
Yes.
you're automatically adding 8 instead of the 7. I just was wondering why.
You add electrons up to the octet.
Always.
Always.
Regardless of where
Yep.
you're-
We don't care about how many valence electrons it has. We put electrons in up to the octet because that's what we're trying to get to.
Okay.
We're trying to satisfy the octets for each and every atom.
Then if that's what we're doing, then why do you need number 4?
Because depending on the structure, you may be adding more electrons into other atoms. And I think I can come up with a problem. It's not on here, but I think I can come up with a problem where we'll run into that situation. In fact, I know I can. I'll show you one in just a second. So if we go through and do NH4, we'd again whip through this one. Nitrogen, 5. Hydrogen has 1. There's 4 of them. Okay? The added caveat in this is what is the charge in this case? Positive 1. To be a positive charge, what has to happen? You have to lose an electron. So when we're totaling our valence, we need to subtract 1 from our total. That's how we can become positive. So that is due to our charge being a positive 1. We've lost an electron, which means our total count is 8 electrons. Sorry, was there a question there? Nope. Okay. What's our center atom? Nitrogen. We do have the hydrogens being the least electronegative, but hydrogen can only form 1 bond. Okay, so our central atom must be able to bridge. That's going to come kind of from experience. Unfortunately, that's all I got for you. So we'll put nitrogen as our center atom. We'll scatter our hydrogens. Okay? And now we want to put in our valence electrons. Yes, sorry?
If the charge goes a +2, will we subtract 2?
Good question. If the charge is +2, what should you do? Subtract 2. We're trying to get our total valence to work out. Oh, geez. It's a lot closer. Okay. We're trying to get the total count to come out. So if it's a +2, I need to remove 2 electrons. What if it's a -2? I need to add 2 electrons, okay, to account for that charge imbalance. Now we can go through, yeah?
How do you know that nitrogen goes in the center?
So this one's a little bit tricky. Our center atom will always be our least electronegative. Okay, well, the least electronegative that can bridge is the subcategory. You haven't had a lot of experience with it, so you don't know what atoms can bridge. Hydrogen can only form 1 bond. If it can form only 1 bond, can it bridge 2 things? No. So that means hydrogen's out as a choice. What's left? Nitrogen. Okay? So hydrogen will always form just 1 bond. It cannot be a center atom.
Will
Yes.
we only need to know that the hydrogen can't bond, or are there other ones we need to know?
For the exam, you just need hydrogen. Not true. Well, your halogens are super electronegative, so they'll never be the center atom anyway. But your halogens can only form 1 bond as well. Okay. More questions before we start adding electrons in. Okay, where do we start adding our electrons? Which atom is the most electronegative? Nitrogen. So we'll now start adding our electrons in pairs until we've satisfied our total valence. How many electrons are around my nitrogen? 8, which means I'm done. Okay, now whenever I have a pair of electrons between atoms, what do? Convert it into a bond. Everybody loves this method because it involves lots of erasing. It's awesome for me. I just move a little cursor over the top of it. Okay? We now have all of our lines converted into bonds. Now we've got to satisfy octets. How many electrons are around the nitrogen? 8. So it's good. How many electrons around each hydrogen? 2. Is that 8? No. What's the issue? Hydrogen can't hold 8 electrons. Look at its energy level. It's in the 1 energy level. What's the maximum amount of electrons we can put into the 1 energy level? 2. So that is hydrogen's octet. 2 electrons. We're done. Okay. Last part of this, since all of our octets are satisfied, we can go through and do our formal charge. What you're responsible for doing for your formal charge is assigning it to the whole molecule. We usually drop in brackets, and we would say the formal charge on this molecule is, how do you know it's +1? That's what our formula was given to us as. It's NH4+. Okay? Questions?
Why didn't it change it when you subtracted the 1 electron?
So subtracting the 1 electron makes sure we get to the +1 charge. Okay? So our structure has already taken that into consideration. When we draw it out, we have to make sure that when someone looks at it, they know, oh yeah, this is a +1 charge.
Right.
Hi. Let's get to Jeremy's quick example, and then I'm going to make you work on OH- and SO3 on your own. Let's real quickly do N. Well, we've already done fluorine. Let's switch that up. NCl3. That's a C with an L, not a U, just in case. Okay. Nitrogen has how many valence electrons? 5. Chlorine has 7. All we're worried about is that column. I don't care what row it is, what column is it? Okay, how many chlorines are there? 3. Okay, 7 times 3, 21 plus 5. 26 electrons need to make it into my structure. Okay, questions about that count? Is that a different question?
Yeah.
Not to do with this?
Oh, yeah.
Okay, sorry. You can talk to me after class. What's our center atom? This one's tricky. Right. Chlorine is closer to fluorine than nitrogen is. Much closer than nitrogen is. So our chlorine is effectively our most electronegative, which means nitrogen's our central atom. Okay? So that worked as kind of a hand-wavy argument. If you pull up the tables of electronegativity, I'm pretty sure I'm wrong. Okay? What did we say earlier about all of our halogens? Jorge, do you remember? Because you just asked.
They only bond, they can't bridge.
Only one bond for everything within our halogen column, which means they can't bridge. So regardless of what our electronegativity says, they cannot bridge, which means nitrogen must be our center atom. We can then scatter our chlorines around. Okay, and we'll start putting in our electrons. Okay, where do I start putting the electrons first? The electrons go to the most electronegative, which is our chlorines in this case. Okay? We go to the outside in this case. So our chlorines now get 8 electrons around them. And now we're going to run into the situation that you were asking about earlier, Jeremy. How many electrons have I put into the structure? 24. How many electrons do I need to put into the structure? 26. Can I put any more electrons on the chlorines? Why not? They've already achieved their 8 electrons. I cannot put electrons onto the chlorines. Which means, what do? We'll put them on the nitrogen. Okay? Which is, I'm pretty sure, the case that you were asking about, Jeremy. What happens when we have more electrons to put in? We find a place to put them. We can now go through and convert pairs of electrons between atoms into a bond. Okay, check octets. Do all of our atoms have 8 electrons around them? Yep. We now have our final Lewis structure. Good job. Round of applause. Good job. Okay, some people wanted to volunteer. That's okay. So, let's give you till 9 to work on OH minus and SO3. Okay? Go through the same rules, apply it as best you can. OH minus is a little bit trickier because we have the negative charge. SO3 is trickier because we run into rule 6. Okay? So if you got questions, raise your hand. Hopefully, I'm just going to draw up the answer for OH minus. I'll draw up the answer for just the SO3 too and see how well people did, and then we'll work through it. So OH minus, answer should be this.
Can we put a circle around the charge?
So I circle charge. Why might I circle charge?
Make it more noticeable.
I'm trying to make extra clear that that's a charge and not a mathematical manipulation. So if we did a reaction where it was H, okay, I need to stop circling for the moment. Let's try that. H plus plus HSO4 minus, okay, that can get a bit confusing, at least for me. So what I do is I will always circle charges. You'll notice when they're multiple charges, plus 2, plus 3, minus 2, minus 3, I tend to not circle those as much. That's just because they get too big for me to circle. Yes, I know that's a silly thing to do, but that's what happens. Okay? Along the lines of charges, let's pick oxide ion. What will we write for oxide? The formula. There's no H. The D ending should be a tip-off that we're looking at just the element. So we've got oxygen. But it's not just oxygen because we put IDE in there, which means we're looking at the ion of oxygen, which happens to be -2. You'll notice that I always write it this way. Is this the way the textbook writes it? They write it O2 minus. Okay. Both ways are valid. I accept both methods. I think the 2 minus, agree with Amanda on this one, I think is stupid. Okay? So I go with the minus, charge first, then the amount. Okay? Entirely up to you which one you want to use. You will always see me do charge, or sorry, sign, then number for our charges. Okay? So How'd you all do with the OH minus? Did you get that one? Good job. SO3. Okay, and you might want to hold your cheers for how well you did in the second here. Because this one's actually kind of complex. And it's going to take me a while. Here I would hope I'm done, but I'm still not. What is the correct answer for this question? All three. If you specify only one, you are technically only a third correct. Okay. Why? This is resonance. This is why organic students hate resonance, because they look at it and they say, well, what's the difference between those structures? When we're looking at resonance, we freeze the location. These atoms now cannot move. Where's the double bond in this first structure? Between the sulfur and top oxygen. Where's the double bond in the other case? The right. Where is it in this last case? To the left. If that structure cannot rotate, has the double bond changed locations? Yes. All three of those structures must be drawn to get full credit for SO3. Maybe. Okay. Resonance is absolutely a harder topic. And because of that, I will grade much more leniently when it comes to resonance. So what I expect you to be able to do is to follow your Lewis structural rules as appropriately as you can. And if you happen to catch and realize there's resonance, great for you. I'll give you some bonus points. If you don't see the resonance, as long as you've done everything else okay, good job. I'll give it to you.
So if it was negatively charged, you'd have to put brackets around.
I'd have to put brackets around all of them. Yep.
Can we do one
Okay.
more example of this?
Well, I'm actually going to argue that what you just saw was a horrible way to show you this.
Okay.
Because what you look at there is the answer. And yeah, you go, oh, well, that's the answer. If you follow the protocols, you can see how that answer falls out of the protocol. So we're going to go through and now solve it from the steps that I told you to go through and follow. Okay? Erase. So, SO3. We'll total it up. How many valence electrons does sulfur bring in? 6. How many valence electrons does oxygen bring in? How many oxygens are there? So we can times 3, which gives us a total of 24 total electrons need to go into my structure. Can now go through and decide which is our center atom.
Oxygen?
It's going to end up being our sulfur as our center atom. We can then scatter the oxygens around it. You'll notice that when I drew up the answers, I tweaked the shape a little bit. We'll talk about shape in just a little bit as well, which won't be on this exam, which is why I'm pushing that homework back. All right? So what we could go through and do is go with our standard format, putting our oxygens on 3 of the faces of this structure. All right? We can now go through and do what? Add our electrons. Where? To the oxygens, because oxygen is more electronegative than the sulfur. Yep. Oxygen is the second most electronegative element on the periodic table. So, second to fluorine. Okay. We've added all of the electrons. So we've finished now step 4. We've added our total electrons. We cannot add any more electrons. So we can now go through and convert any pair of electrons between into a bond. And now we want to go through and check our octets. The rightmost oxygen, how many electrons? Top oxygen. Left oxygen. Sulfur. 6. Here's where most people mess this up. If you start with the central atom, you'd put a lone pair Oh, now it's satisfied. Except what did I just do?
Added 2 more.
I added 2 electrons. My electron count is now 26, not 24. We can only put in 24 electrons, which means we cannot randomly add that new lone pair. This is why we moved to rule 6. We now must satisfy the octet by moving a pair of electrons. And what do we mean by moving? Well, let's go to an oxygen. I'm going to pick the rightmost oxygen just because it happens to be on my screen. And I'm going to erase that pair, and I'm going to put it on the sulfur. How many electrons does sulfur now have?
8.
Good. We solved our problem, right? What's the issue? Now the oxygen has 6. So I somehow need to move that pair of electrons in such a way that it can count for both the sulfur and the oxygen. I make it a bond, because the bond allows for the sharing of the electrons. So what I'm going to do is move that electron pair into a bond now between that rightmost oxygen and the sulfur. How many bonds do I now have between the sulfur and the oxygen?
2.
What might I call that interaction? A double bond. We now have the birth of our multiple bonds. Okay? If you follow this method, it sets you up where you naturally see multiple bonds needing to show up in the structure. If you go through and solve it any other way, you do not see this natural progression. Okay? And you end up just having to guess at it, which works fairly well. Okay? There's plenty of chemists that have gone through and have lucked themselves into drawing Lewis structures and then have done enough experience with Lewis structures that they can continue to now guess their way through very, very well. That's awesome for them. You're not at that position yet, which is why I'm trying to set you up with the rules to make sure you can consistently and accurately make your way through it. Okay? Questions about that?
So that's not the answer.
So that's the last question. So any questions about what's drawn up there first? Okay. So yes, Jeremy, you're right. What's the issue? I said we needed 3 drawings, and I've only shown 1. So let's take a step back to what I had initially had drawn. Why did I pick the rightmost oxygen? Is it different from any of the other oxygens? No. So couldn't I have used the topmost oxygen? Yeah. Couldn't I have used the leftmost oxygen? Yes. Which means, since all of those are equally likely to occur, I must show all of them. That is what resonance is talking about. We end up with the same arrangement of atoms, but what we've done is change the location of double or multiple bonds. Okay, either double or triple bonds. For what you guys are concerned about, you will probably only see double bonds shift around to generate resonance. Okay? This is a massively tricky concept. So if you don't get it now, don't panic. Okay? Focus on getting the rest of the rules correct. Don't stress about the resonance. Okay? When does it become hugely important? Anybody that has to touch organic chemistry, it's resonance. 2 answers in organic chemistry pop up all the time. Someone asks you why in organic chemistry. Your first answer should be electronegativity. Don't say anything more than that unless they fish for more. Okay? Because then you can sound like you know what you're talking about. You don't have to worry about actually knowing why. Okay? So you can just say electronegativity. That covers maybe 60% of your answers. 40% of your answers, or 49, 39, I can do math. 39% of your answers is resonance. Okay? You don't need to know anything else about organic chemistry. You've now covered 99% of the questions that could possibly be asked of you. Okay? Pretty amazing how much space just being able to look at structures covers when you're looking at the balance of resonance and electronegativity. Questions? Thought I saw a question. Yes?
The location of the electrons is not super significant. Like you're taking them off the bottom of one, the top of another.
True. Any of the pairs of electrons on a single atom are all equivalent. It doesn't matter which pair I move. Okay? So if I was going to draw this all out again, I would have to go through and specify the other 2 options and tag all my lone pairs onto it. Okay, for this. Do I have to draw it again? Okay, thank you. I'm not going to draw it again. Okay?
Yeah, my question was just about when you're with your double bond, if you've got 2 on the top, 2 on the side.
Yeah, it doesn't matter from an individual atom which pair of electrons you move. Okay? Do you still want another example on resonance? Okay, thank you, because that was going to be a stretch.
So if you have more than 4 atoms, would you?
So, very good point here. Can we have more than 4 atoms around a central atom? Each bond brings in 2 electrons, right? 2 electrons means a total of 8, which means no. We would say no way in hell are we getting more than 4 atoms around an individual structure. Is that true? No. We can put more than 4 atoms around it. For the sake of this first exam, how many atoms can you put around it? 4 atoms. I was like, where did 8 come from? Or 8 total electrons. Okay? After this exam, okay, we'll talk about some more examples where you can exceed the octet. To exceed the octet, what we have to do is get the atom big enough that we can fit more things around it, which means we have to move into our higher energy states. Okay? So energy level 3 or lower on the periodic table, so 3, 4, 5, 6, all of those can expand their octet, meaning they can fit more than 8 electrons around them. I know, that's tricky. We'll talk about it when it shows up in lab. I don't think I will ever test you on it in lecture, as far as drawing Lewis structures go. Yes?
Will your center atom always be the one that does not have both, is not a multiple atom element? So
I'm
when you're,
confused.
when you're going down through your steps, if you have like the SO3, the oxygen has 3, so that has to be on the outside. Is that
Yeah.
a good way to look at it?
Yeah, I can accept that. That works. At least for the examples that we'll see. Yeah.
And then just electronegativity, I'm just a little confused just because like of the nitrogen and the chlorine, the first like the example right before this was kind of confusing.
So one of the things that you'll start to pick up, particularly as you draw more and more structures, and that really shows up in organic chemistry, is when you start to try and predict what's happening. And in those predictions, we make some pretty drastic simplifications. Those simplifications are that everything in that last column, our halogen column, so our second to last column officially, we consider as the most electronegative. It isn't technically true, but as a first approximation, it works. Okay, so when I go through and say chlorine is lower in electronegativity than oxygen, that one's actually technically true, because oxygen is the second most. As far as that balance between those two, you start to make approximations where is our halogens can only form 1 bond, which also isn't technically true. Okay? But we make those simple approximations because what we're looking at is in those first 2 rows, if we settle in just those first 2 rows, all of our Lewis structures get drastically simplified. Okay? And that makes life a lot easier to worry about. If you move into organic chemistry, how much more complicated does it get? It does not get more complicated. You stay in those first 2 rows. You only have to worry about 4 things attached to an individual atom. If you move into Gen Chem, what happens? 151. Sucks for you. It gets more complicated. Okay? So depending on what applications you're looking at, you'll look to different extents. General chemistry looks at the entire periodic table, which means you need to know everything. Am I recording? Yeah. Organic chemistry, we're a little bit simple-minded. We can really only deal with roughly 10 elements because we only have 10 fingers. We simplify to that very top row, and we make drastic simplifications elsewhere. Okay? Because we can't deal with complexity. Okay? Anybody that moves into organic chemistry may beg to differ, okay? But that's kind of the bottom line of it. We really try and simplify things down. Okay? Other questions? Okay. With Lewis structures, it really comes down to practice. Okay? If you don't get enough practice now, if you move into organic chemistry, you're going to get forced to do even more practice. So you need that practice to be comfortable with the structures. You end up stop counting valence electrons. You end up taking the shortcuts that you watch the tutors go through and do, that I went through and did with SO3, and drawing all those double bonds in and just being happy with it. Okay? Because you're comfortable with how many electrons belong in the structure, you don't make those simple mistakes. Okay? Until you've done that practice, these are the rules, follow them. Okay? They are different from the textbook. They are different from what the tutors present. Okay? That's because they're all focused in Gen Chem. Sorry, It's either a good thing or a bad thing for you. I'm focused in organic. I'll set you up with the rules to move through and actually understand how molecules interact, not just follow dumb rules. Okay. Notice I said not just follow dumb rules. Okay. Questions? Okay. I personally think that went really well. I don't know what you guys did, but I thought that was nice. Okay. Lewis predictions in reality. All right, so this is where we're going to bring in the concept of shapes. I am going to lecture on it. It's not going to directly show up on the test. Okay, so you are not personally responsible for this material on the test. You may see some questions show up. They just won't affect your grade, sort of. So you can think about what that means on your own. Okay? So if we provided the Lewis structure for methane, CH4, okay, we could real quickly draw that out, because you all are lightning quick at drawing Lewis structures now. And we got our Lewis structure for methane. Okay. Are any of those hydrogens different from any of the other hydrogens? No. So they're all exactly the same. Okay. What happens when we bring two hydrogen atoms near each other? Okay. Both hydrogen atoms have a nucleus. What do those nuclei do? Positive, positive, and they go, get the F away from me, and they spread away from each other. Okay? You're kind of right with the bond. Let's ignore the bond. Okay? So let's assume they can't bond. So if we take a look at these hydrogens, what ends up happening? Well, our top hydrogen is going to get as far away from the hydrogens on the side as possible. Okay? So what we would expect is each of those hydrogen atoms to spread as far away as they possibly can. And because they're all the same, what should the distance be between each and every single one of those hydrogens?
The same.
The exact same. Okay, well, let's test that theory. What we'll do is look at a bond angle. What's the bond angle between that hydrogen, carbon, and hydrogen? 90 degrees. How about that one? 90 degrees. Hey, this is looking pretty good. This one? I'll do that one a little weird, but still 90. Last one? 90. So we say, okay, theory's correct. They're all as far away from each other as possible. Is there another bond that I didn't look at? What's the bond angle between those two hydrogens? 180. Are they all equally spaced away from each other? No. Lewis structures do a great job of explaining how atoms connect to each other. It does a horrible job of explaining where those atoms are relative to each other. Okay? So what we're saying is a shape. The shape that we've drawn for our Lewis structure is necessarily drawn in what plane? Or how many dimensions? 2 dimensions. Is everything we do in 2 dimensions? No. Everything is 3-dimensional. Okay, so those of you with really good geometric minds, what shape comes out of this? We've got 4 points that all need to get equally spaced away from each other. The shape that we generate is the for tetra, I think because it's a shape, tetrahedral. Okay. So Lewis structure doesn't explain the shape appropriately, because when we draw that out, that does not look like a tetrahedron. Okay. How do we know what a tetrahedron looks like? Well, this is where model kits come in handy. We're going to use my goofy hands. There's 3 bonds with my fingers. Okay. That 4th bond is going to be my wrist. Our tetrahedral shape, like that. Where the center atom is the knuckles of where my carbon is, and everything else is the bonds out to hydrogen. So there's our tetrahedral shape. If I tried to draw that in a plane, what ends up happening? Is this in the plane of where I'm drawing? What we'll do is put the iPad as my paper. Where's that atom aimed? My middle finger, sorry. Where's that aimed? It's not on the paper. For you guys, it's aimed towards you. How could we draw our structure to represent that it's aimed towards you? What happens is things get really close to you. That worked. That was fun. It gets bigger. Okay, so when we draw out our structure, what we're going to try and do is represent that that atom is getting bigger. We'll always end up with 3 atoms in the same plane. But one atom is getting bigger. There's your super awesome artistic chemist. This wedge shape coming at you with our hydrogen. What happens as it gets further and further away? It gets smaller. How can we represent that? We use the dash shape. What we're now trying to draw is the three-dimensional object. Okay? And we've had to imply what those things mean. Is it tricky? Yes. Okay? Don't stress too much on drawing it because your exams are multiple choice for the most part. Okay? So focus more on the Lewis structures than anything else. Okay? So when we went through to try and predict this tetrahedral shape, what we did is took advantage of how we would expect those atoms to interact with each other. We looked at electron-electron repulsion, or proton-proton repulsion. Officially, it's electrons. Why is it electrons? Those are the first things to interact. Those are the first things that our atoms would see from each other. Okay? So what we're looking at is how our electrons repel each other. What type of electrons we're repelling? The valence electrons. So what we're looking at is the valence shell electron pair repulsion theory. Okay? How do those electrons push against each other to force the shapes of our overall molecules? Okay? So when we go through and look at individual systems, we're going to end up with two possible geometries that come out of this. Something known as the electron geometry. Okay? That shape is going to be determined based on the groups of electrons around an individual atom. For you guys, it's going to be around our center atom. We'll always focus on the center atom. We don't care about any of the others. The molecular geometry goes through and looks at that same shape, except anywhere that there's electrons not in a bond, or actually anywhere there's not electrons. Should I try and rewind that back? Okay. What we'll look at with the molecular geometry is just where the atoms are located. So we don't care about the electrons. That's going to cause a slight change in how we name the shape. How do you go through and decide these? That's going to be based on memorizing what the different shapes look like. And those different shapes are things that some chemist or artist sat down, looked at, and said, that looks most like this shape, I'm going to call it that shape. Okay, that's where they came from. Okay? So, sorry, you guys are still writing. So if we looked at CH4, we said it was a tetrahedral shape, right? Because we had 4 atoms around it, all equally repelling away from each other. If we switch that thought process around a little bit, we had 4 bonds. So it's not the atoms, it's actually the bonds. It's those bond electrons that get near other bond electrons and say, get the hell away from me. And they spread out into that geometric shape. What happens if we move to something like the NH4? Well, our central atom is a nitrogen, and we have our 4 bonds again around it. What shape do we expect for this? Same as for carbon. We get that tetrahedral shape. What happens if we switch it up one more time and we jump to NH3? The Lewis structure for NH3 gives us this. So if we're looking at the electron geometry, how many groups of electrons are around that center atom? 4. So our electron geometry is tetrahedral. It's the exact same shape. But when we move to the molecular geometry, what do? We ignore the lone pair. Now all we care about is what happened with the other atoms. Okay? We end up calling this a different shape. Okay? And that's really where our difference between our electron and our molecular geometries come from. So what we've got here is the number of electron groups, a representative molecule, and the shape that comes out of it. You are responsible for up to 4. Whoops, that's not a pen. Okay, you're responsible for this section. Okay, the trigonal bipyramidal and the octahedral will show up after exam 2, for sure, and I don't know that they show up on the final, so you may not need to worry about them at all. Why would we kind of avoid those right now? how many atoms are around our central atom? 5 and 6, more than 4. So what we talked about already is that we only can deal with 4s at this point. Okay, so we will come back to looking at those after exam 2. Okay, so let's pick an example. If we looked at HF, all right, let's color that in. Our electron geometry is what? In the electron geometry, we look at our center atom. Our center atom in this case is tricky, but fluorine. We look at the geometry around it. Okay, our electron geometry is what? How many groups of electrons are around it? So look at the 4 faces of the fluorine. How many distinct groups do we have? 4. So that shouldn't say electron geometry. That should say molecular geometry. Our electron geometry is what? Tetrahedral. What's our molecular geometry? Now we just look at how 2 atoms can arrange around each other. What shape do we get when we connect 2 atoms? Linear. What if we turn it on top? It's now just a straight line going up. It's just the linear shape. Okay? So what we're looking at is how do each of these class out? And yeah, I should have caught that mistake. I'll fix that for after the exam. So let's draw a second column for our electron geometry. Actually, I wonder, did I put it on there? Let's not look at that yet. Our electron geometry for HF ends up being tetrahedral. That was a bad example. Let's run with, oh, here's how I can fix it. What can give us a linear, got it. Not HF, but HH. What's the electron geometry? How many electrons go into HH? 2. Where are those 2 electrons? In the bond between the hydrogens. So we have 1 group of electrons, linear. Okay. MgCl2, what's our center atom? Magnesium. So we could drop our magnesium in. Here's our chlorines. All our electrons. We real quickly whip through that. Convert them into bonds. How many electron groups around that center atom? 2. What shape do we get? Linear. We're trying to get those 2 objects as far away from each other as possible. As far away as possible is 180 degrees. Okay, completely linear. What happens in the case of BH3? Okay, this is one of those trick ones that you won't see on the exam. Anybody remember what the trick was with boron? Has to do with its octet. It does not have to have 8 electrons. Boron's happy with 6. Okay. So when we look at our Lewis structure for BH3, how many electron groups? 3. The shape that we get out of that is trigonal planar. Okay. CH4 we just talked about. PCl5, one of the reasons, or CH4 and down, 4, 5, and 6 groups, are really, really difficult to draw because those shapes necessarily involve 3 dimensions. 3, 2, and 1 are all 2-dimensional shapes. We can get away with just drawing those flat. So those are relatively easy to draw. Okay? Depending on what images you get out of it, okay, I happen to like this figure. What this figure is showing is those geometries all the way through. The one issue, man, stupid figure, didn't quite match up. We needed 2 linear shapes. Okay, because the linear shape showed above has how many electron groups? 2. How do you know there's 2 electron groups? You see the 2 lines connected to that red atom. Okay? So what we're now doing is moving from Lewis structures and now interpreting those Lewis structures into shapes. That involves a pretty big leap. Okay? And a lot of it's just going to come down to having it memorized as to what things mean what when you go through and look at it. Okay? So we just talked about this example. Are all electron bonding groups or electron groups the same? Bonding versus non-bonding. When we look at NH3, we've got our center atom of nitrogen. We've got our 3 hydrogens. Whoops. Scattered around it. We drop in our 8 electrons that we counted from it. That only gives us 6. Where's that 6 or the 7th and 8th electron? On the nitrogen. If we look at just the groups of electrons, how many groups of electrons are around that nitrogen? 4 groups of electrons, which means what electron shape? Tetrahedral. When we move to the molecular shape, all we care about are the atoms. So now we would look at how the hydrogens are arranged around that nitrogen. Well, we say, well, there's only 3 atoms, so it's got to be trigonal planar. Does that work, though? The atoms are forced into their locations because of this lone pair. We're not going to change the orientation once we ignore the lone pair. So we're still tetrahedral as an electron geometry, but our molecular geometry now must be a subset of our tetrahedral shape. Okay? So within that, we lose that lone pair of electrons, and we now look at a different shape. So if we went back to that tetrahedral shape of my hand, and we now don't look at an atom for my wrist, what shape do we kind of have? It's very similar to tetrahedral, but for tetrahedral, I need something up top. There's nothing up top. Sort of a triangle, but if it was just trigonal planar, it would be flat, and it's not flat. It looks kind of like a pyramid. The molecular geometry for NH3, trigonal pyramidal. How do you know that? Because some fancy person came through and told me. I'm that fancy person. What's that? But it's a trigonal pyramid, which means 3.
Right, no, that's what I'm saying. That's the
Yeah.
difference.
Okay? So, all of those shapes that you all looked at and you're like, oh my god, that's way too much for me to even remember. And now all of a sudden what I do? Would I double it? Yeah, pretty close. That big red line is representing what? You need to remember above it. What about below it? Do you have to do 151? Then don't worry about it. Do you have to do 151? You should start thinking about it. Okay? For this exam, we're not going to stress too much on the shapes. I wanted to lecture on it. We'll go through and look at a lot more examples of it as an ultimate simplification of this. Okay? And I know everybody goes, well, how is that even more simple? Trust me, it is. Look at your structure and decide how many groups of electrons are around your central atom. You'll notice this is just 4 groups. If you've got 3 groups of electrons around it, you'd move to our 3rd column, and our electron geometry is trigonal planar. What happens if you then look at that structure and not all of those 3 groups are bonds? Well, that's what's happening in that next column. If we have 3 groups that are all bonds, what shape do we get out of the molecular? Trigonal planar. What if we look at that shape and only 2 of them are bonds and 1 of them is not? You get a bent shape. Right? So you don't have to be able to draw or apply it. You just have to be able to look at it and say, how many groups of electrons around this atom? What can I do with it from there? Okay? So please breathe. It isn't that bad. When determining shapes, you're looking at pretty much just this slide for the full summary. Okay? When it comes to Lewis structures, you are responsible for drawing Lewis structures. You do a lab next week. Perfect timing to do it next week after you're responsible for it. Okay? Please take a look at that lab and start doing some of the simple examples. I will say that some of those examples are stupidly hard. Okay? So be a little bit careful with that. Talk to people. Try and do some practice within these structures. If you have questions about what types of structures I'm going to ask, you might go through and take a look at some of the examples that we talked about. Right? Because I think those examples were simple enough for you guys to do in class. Might be a reasonable guess that I'm going to pick structures that are similar to these. We still officially have 2 minutes, so if you've got questions. The element project is officially due at the end of the semester, last day of class. there's an outline that's due the 21st. Due the 21st. Due the 21st.